This is VLSI data conversion circuits, lecture 12. In the last class we were looking at how to estimate the spectrum of a sine wave, right, given that the input frequency is known and the sampling rate is known, and we are trying to characterize a sample and hold, and we said that the input frequency cannot be chosen in any old way. Fin by Fs must satisfy m by n, where n is the record length, right, and m must be an integer. Okay. So, if this condition is satisfied, then if we find the discrete Fourier series corresponding to the length n, you will get n coefficients of the discrete Fourier series, and if this relationship is valid, then you will see only one coefficient being non-zero, all the other coefficients will be 0. In practice, the other coefficients will be very small, corresponding to numerical precision of the FFT computation, right. And as I was mentioning to you last time, n is called the record length, and often chosen to be 2 to the power of p, where p is an integer. The advantage being that it turns out that they are very fast algorithms to compute the Fourier series coefficients if the record length happens to be a power of 2, right. And as we saw, each one of these Fourier coefficients is what is called a frequency bin, right, and therefore, since there are n coefficients and this spans a complete frequency range of 0 to Fs by 2, right. In Fs by 2 there will be n by 2 bins, which therefore means that the width of a bin, right, in real frequency terms is Fs by n. So, we were wondering what would happen if the input frequency or the input tone did not lie on a bin. In other words, if Fin by Fs is not m by n, but there is a fractional part to m, and we saw the last time around that when the input tone does not lie exactly on a bin, there is something called leakage, right, and that is happening because one can think of it as follows: the discrete Fourier series is nothing but a sampled version of the discrete time Fourier transform, right. If the sequence is a finite length one, the discrete Fourier transform of the sequence is simply the infinite extension multiplied by a rectangular window of length n, which in the frequency domain corresponds to convolution of the original spectrum with that of the window, correct. So, in other words, if we had a sinusoid which was not on a bin, let us say, so if the input is of the form a cos of a n, where small a denotes the frequency, and we are only taking a finite number of samples, say capital N samples, then the Fourier transform, the discrete time Fourier transform of this sequence is nothing but the delta function convolved with the spectrum or the Fourier transform of the window function. Since you are taking only a finite window of samples, it is equivalent to having a window which is the so called rectangular window, and as we saw the last time around, the spectrum or the Fourier transform of the rectangular window is a sinc pulse. So, what we are in effect having for the finite length sequence is one which has a Fourier transform which is these impulses convolved with the sinc pulse. Okay. So, in other words, it will look like this. Let me show you a picture. Right. And if the input lies exactly on a bin, what happens? This is the discrete time Fourier transform of the windowed sequence. What we are doing is computing the discrete Fourier series coefficients of this sequence, right, and as we saw the last time around, that is nothing but a sampled version of this. Now, if the input lies exactly on a frequency bin, then we will be sampling these points right, and which is why it makes sense that when you have a rectangular window and the input lies on a frequency bin, which is equivalent to saying that f in by fs is of the form m by n, you will see only one coefficient which is non-zero when you compute the discrete Fourier series of that sequence. Now, if the input is not on a frequency bin, in other words, f in by fs is not of the form m by n where m is an integer, then what is happening? This small number a is no longer of the form 2 pi by n. So, what we are doing is essentially sampling the spectrum slightly off center, if you want to put it that way. So, for example, here, 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 here and so on. And when you look at the discrete Fourier series coefficients, please note that this is a linear scale. Okay. What you will see is something of, you join these points, you will see something like this. Is this clear? Okay. Now, as a side point, if the deviation from the bin was originally delta, okay, that corresponds to this deviation, right, and if the deviation increased to 2 delta, what can you say about the level of the leakage? It increases, right, by how much? Earlier, let us say the input tone was 127 by 1024 plus say 0.01 times fs, and naturally we expect leakage because the input does not lie on the exactly on the bin, correct. Now, if I make this 127.001 by 1024, now also we expect leakage for precisely the same reason. Now, where do you think the leakage will be more? You had two frequencies, let us say 127.01 by 1024 times fs and 127.001 by 1024 times fs. Where do you think the leakage will be more? Obviously, this will leak more, right. The question is how much more. This is just a side point, but I thought it is quite interesting to Can you look at the diagram and tell me? This is a linear scale. Yeah, of course it is a ratio of the sink values, but can you get more specific than that? If you are exactly on a bin, what will the leakage be? 0, right? So that is you are here. If you deviate slightly from that position, what happens to the Fourier coefficient? As you can see from the picture, it will increase. For small deviations, it will be linear, right. So whether, I mean, so when you compare the leakage of 127.01 versus 127.001, what should you expect? You should expect to see a leakage which is 10 times more in one with respect to the other, right. That day I thought we were going through this example. Okay. We discussed this the other day, right. I mean, one of them was a tone of frequency 127.01 by 1024 times Fs, and the other one is 127.01 by 1024 times Fs, and as we expect the leakage is smaller, right. The other day we made wild guesses and said one is 127.001, right, but it indeed makes sense that what we should expect is the leakage should go down by a factor of 10, right, which is 20 dB. This is a log scale, mind you, and definitely the difference is 20 dB. Is this clear? All right. So the moral of the story so far is that if the input and the sampling rate are synced, in other words, it is possible to somehow make sure that Fn by Fs equal to m by n, where n is the record length and m is an integer. If it is possible to do that, then the input frequency will lie on a bin and there is no problem, right. And please mind you, this is just simply trying to capture an input sinusoid. We have not talked about more things which happen in practice, which is noise and all this other stuff, but simply to capture a sinusoid and make sure that from the samples we are able to figure out what sinusoid it is, all this has to happen, right. And since we are on the topic, we might as well discuss what happens in those practical cases where for some strange reason or the other it is not possible to make the input and clock in sync. I mean, as we discussed the other day, to make the input and clock in sync, it is trying to set your watch and your friend's watch to be exactly in sync, which means that periodically one would have to sync up both their watches either to a master reference or to each other, right. You understand, and that is a negative feedback system. If you are going too slow, you speed yourself up. If you are going too fast, you slow yourself down. Such a negative feedback system is what is called a phase lock loop, and we will not go into the details in this class, right. But sometimes it is simply not possible in order, I mean, that the clock source and the input sinusoid are able to talk to each other and sync themselves up. Then we need to wonder, what to do, right. So fat chance that the input tone and the sampling rate will be exactly related by m by n. Even if they were related according to an integer ratio at some point in time, soon enough they will drift away and the relationship will no longer be valid. So, we need to figure out what we need to do to fix this problem, right. In other words, if this ratio is not satisfied, how do we, I mean, what do we do with the sequence, so that we at least try to mitigate this so called leakage to some degree, right. So, before we get to the solution, let us kind of look at the problem in another light, which is in the, let us try and interpret this in the time domain, right. So, if the input sinusoid lies exactly on a bin, correct. Please note that the discrete Fourier series, all it is doing is making a periodic extension of the sequence that you have, right, and computing a Fourier series of this periodic sequence, correct. Now, in other words, if the input was on a bin like the sinusoid in blue here, right, let me show that to you. When you make a periodic extension, what do you think will happen at the end points? I mean, in other words, when you make a periodic extension, there will be no kinks at the edges, right. Whereas, if the input sequence does not, or the input sinusoid does not lie on a bin, what happens at the end points? What you will see is some curve in, an example of that is shown in red, right, where at the end point, I mean, it is not periodic obviously, okay. So, at the end points there is a discontinuity. Can you comment on the magnitude of this discontinuity as time progresses? Let us say I took another set of 1024 samples. Do you think the discontinuity would be the same? It will be different. Why? Simply because the sequence is not periodic, correct. So, when the input tone does not lie on a frequency bin, what you must remember is you are finding the discrete Fourier series corresponding to a sequence like the one shown in red, where at the ends of the sequence there is a discontinuity, right. A discontinuity is nothing but an impulse, correct. So, there is a jump here, and how frequently does this jump occur? It occurs every n samples. This corresponds to a fundamental frequency of, I mean, 1 by n samples. The periodicity of this jump is 1 by n samples, and whenever you have a jump in a signal, what can you say about its frequency components? There are a lot of high frequency components. In other words, even though the fundamental frequency of this jump is 1 by n samples, right, it will have a whole bunch of harmonics, correct. So, this jump is what is responsible for causing leakage when you take a rectangular window. Does it make sense, right. So, every n samples you have a jump, correct, and the jump consists of impulses which has got a lot of high frequency content, right, and that will simply, the jump and its harmonics will now add to the spectrum of the sinusoid. Is this clear? Yes. Okay, so now that we understand this, let us try and figure out what we do about this problem. So, we have a record length. Please note that even though these are all sequences, I will just draw them as a continuous wave, otherwise plotting those sequences is, takes a lot of time. You understand? So, even though I show a continuous waveform, you must understand that these are actually samples. You may perhaps think that there are so many samples that when you plot all those things together, it looks like a curve. So, now we have a situation where we have a fixed window length and the sinusoid is not quite periodic in the sense that there are discontinuities at the ends. When I make a periodic extension of this sequence, there are kinks occurring at every n samples, right. So, the question is, what do we do about this? How do we fix the problem? Any suggestions?
Try to make that discontinuity go to 0.
So, we know that this is all the data in the middle, right, is all seems quite okay, right. It is only the data at the ends which is problematic, right. When we were using a rectangular window, what was happening was that all samples of the data are equally important, correct, okay. But we know that in reality the leakage is occurring because of this discontinuity, alright. It is not fundamentally a problem with most of my data, there are only a few guys in the end who are contributing a lot to this leakage, right. Anytime you have a kink in a waveform, it will show up in the Fourier spectrum as high frequency components or as leakage, okay. Now, since we want this part and we do not want this part because that is the one that is causing leakage, what do you think we can do? In other words, the samples in the middle are important, the samples in the end are not so important. I mean, if you remove then if you chop off the samples in the end, then what you chopped off, right, will become the end, isn't it? That is clearly not a solution. You understand? It is like saying there was some guy who was getting off at a traveling by train and then who got off at the platform to fill water, right, and there was a long line, and by the time he filled water the train started moving, and then you know he missed the train, right. He tried to catch the last compartment and he could not make it, and then he missed the train, and then he lodged a complaint saying, oh, there should be, the problem is with the last compartment, so there should not be a last compartment in the train. You understand? That is I mean, chopping off the ones that you do not want, right, does not help you at all. Okay, so what do you think we should do? So, you say that these are, I mean, all are equal, but some are more equal than the others, right. So, you say, okay, I will weight all these, since all these seem equally important by the same factor, but I know my end guys are not so important. So, I will taper off my weighting function like this and like this. Does it make sense? So, in other words, I will take this sequence, I will multiply it by another sequence which remains fairly constant for all the middle samples, right, and tapers off smoothly to 0 at the ends. You understand? Now, if you do this, what has happened to the resulting sequence? The resulting sequence looks like this. Okay. Does make sense? It simply, this is the so called windowed sequence, the one in red is the original sequence, and this is the window function. Does make sense? I mean, you can think of it as a, instead of using a rectangular window where all samples have the same weight, we realize that the leakage is a problem arising due to discontinuities at the ends. Therefore, what you want to do is to not treat all samples with the same levels of importance. The ones in the middle are more important than the ones in the edges. So, in other words, you multiply this by another sequence which tapers off smoothly to 0 at the ends. It is very important for this window function to taper off smoothly. Why? I mean, if there are discontinuities in the window function, then I mean they will also be present in the windowed sequence, which will again lead to leakage. You understand? So, this is the basic idea behind what is called windowing the sequence before taking its computing its discrete Fourier series coefficients. Okay. And clearly the spectrum of the windowed sequence is not the same as the spectrum of the original sequence. It has to be different because I have taken the original sequence and modified it by multiplying it with some within quotes known function, right. But what one must intuitively expect is that the leakage will be less compared to using a rectangular window, because the discontinuities are now gone. Okay. I mean, it may also do something to our desired signal. Okay. It may make the sinusoid look different, right, but at least we know the window we are using. So, hopefully we will be able to make sense out of what we get at the output. Is the motivation clear for using windowing? Okay. So, if I just draw a window function like this, which says it must be, you know, the samples in the middle must roughly be given the equal weight and the samples at the end must be given 0 weight, and it must taper off smoothly to 0. What do you think? I mean, how many ways are there, do you think, of coming up with a window sequence which can do this? There are any number of ways of coming up with a window sequence, right, which gives approximately the same weight to samples in the middle and smoothly tapers off to 0 at the ends, right. So, corresponding to each one of these things, right, there are any number of windows which are called spectral windows, which are around in the literature. People keep, you know, have discovered and keep discovering new window functions where there is a minor variation here and there, right, but the basic idea is something where which is flat on the top and slowly tapers off to 0 at the ends. So, let us take a look at some common window functions and see their properties. As I said, a window function is job is to start at 0, end at 0, and kind of emphasize the samples in the middle more than the samples in the end. So, one function which kind of does this, I have drawn a very smooth looking curve. Can somebody tell me what kind of, can somebody give me a functional relationship for, well, it's no, a Gaussian can never go to 0, right. So, this looks like a cosine wave, pushed up, right. Instead of going from minus 1 to 1, it goes from 0 to 1. Okay. So, see, you have discovered a window yourself. Okay. So, it's okay. So, this is what is called a raised cosine or a hand window. All right, and is given by half times 1 plus cos one minus cos n by n times this is what 2 pi, right. Okay. So, it starts off at 0, ends at 0, and in the middle it reaches so the average is half, and then this peak is 1, and then goes from 0 to 0. All right. Now, let us see what the raised cosine window does to a sinusoid which lies on a bin, right. Okay. And what do you expect? Earlier when we had a rectangular window, what would be the discrete Fourier series was sampling the discrete time Fourier transform of the window multiplied by the sinusoid, correct. It is the same thing now, it is except that earlier the discrete time Fourier transform of the rectangular window was a sinc function. Now, it is not a sinc, it is something else. Okay. So, this is, please note that this is valid only within 0 to n minus 1. Okay. Does it make sense? Now, so if you had a cos a n and then you multiplied this by this window function which is half times 1 minus cos 2 pi by n times n. This is the sequence whose discrete time Fourier transform is being sampled when you compute the FFT. Is this clear? Okay. So, now can you tell me if the input lies on a bin, what do you think you must get? So, this you can also think of it as being multiplied by, since this only is valid between 0 and n minus 1, you can think of this as being multiplied by a rectangular window of size n. So, what do you think you will get? Pardon? Okay, and those bins correspond to?
Correspond to the fundamental and one to the left and
One to the right. So, as you can see here, cos A n is getting multiplied by half, which basically means that it is simply half cos A n, and it is also getting multiplied by half cos 2 pi by n times cos of A n, correct. And how does this look like? Cos A cos B is, you will have only two components, quarter times cos of A plus 2 pi by n and quarter times cos of A minus 2 pi by n, right. So, if A lies on a bin, A plus 2 pi by n will also lie on a bin and A minus 2 pi by n will also lie on a bin, correct, right, and all the other bins are 0. Is that clear? So, in other words, if the input lies on a bin, then for a rectangular window you would see only how many of those coefficients would be non-zero? One. If you take only one half, there will only be one coefficient which is non-zero. When you use a hand window, how many do you expect to see? You expect to see 3, and where are the 3? One corresponds to the input itself, one bin to the left, one bin to the right, okay. And please note also that there is a very definite amplitude relationship between the main bin and the two side kicks, okay, all right. So, the main bin has a coefficient or an amplitude which is half the input amplitude, correct. In other words, if I had used a rectangular window, I would have got some strength for the bin A, assuming that A was on one of the bins. Now, I will only get half A, right, and then so this is A plus 2 pi by n, what will I get? I will get an amplitude which is 1/4, and A minus 2 pi by n, I will get another amplitude which is 1/4. Does it make sense? Correct. So, in other words, if the rectangular window gave me something like this for that bin, a hand window will give me non-zero values for 3 bins. This bin will be 6 dB below what I would get if I used a rectangular window, and similarly this would also be 6 dB below. Is this clear? Half is 6 dB.
So, what is that half? We don't need a half.
Yeah, I mean we do not need a half. I mean the question is why are we getting these halves, right? I mean thankfully and not surprisingly these multiplication factors you get, right, are all dependent on the input. I mean these are the input amplitude multiplied by these factors. So, in that sense this is not a disaster, because if I know the window I am using, and if I find a by 2 a and a by 2, I know that the true amplitude is 2a. Is that clear? And what can you say about the power of this sequence? The power of the windowed sequence, the power of the windowed sequence is 1/4 plus 1/16 plus 1/16 is the power of the windowed sequence. And when you compare it with the input power, right, I am neglecting the half factors which have to be there, but the ratio of the powers is what? It is, so rectangular windowed so this ratio is 3 by 8. In other words, the power of the windowed sequence is 3/8 the power of the same sequence had it been windowed by a rectangular window. Why does this make sense? I mean, is it something which is surprising, or is it something to be expected? Just to be expected. Why? Great, because we are basically weighting only some samples in the middle by something close to 1, right. All the samples other than those are getting weighted by factors which are less than 1, which means that they contribute lesser amounts to the power. Therefore, it definitely makes sense that the power of the windowed sequence is smaller than, or rather to be more correct, I must say the power of the hand windowed sequence is much smaller than the power of the rectangular windowed sequence. Okay. Now, let me show you a picture. Okay. So, the red one here is hand, whereas the blue is the rectangular windowed version. This is intended to show you that clearly the blue one is ticking slightly above the red one, right. We will zoom in there and take a look, but I wanted to show to you that all the other coefficients are 0. That is only possible if the input lies on a frequency bin, correct. So, when I zoom, this is what you get. So, this is the rectangular window, and this is the hand window, right. And as you can see, this is 6 dB and so are these. Is this clear? All right. Now, let us see what happens when, finally please note that the whole idea behind coming up with this window stuff is to see what happens when the input is not lying on a bin, you understand. Okay. So, and before I go there, let me reiterate the fact that if the input is on a bin, the input power is now spread across 3 bins. So, if you want to find the true input power from the hand windowed FFT, what you need to do is find the power in all the 3 bins and then multiply that by what? 8 by 3, because 8 by 3 corresponds to the power loss of the hand window because of this weighting. Is this clear? Is this clear? Now, let us see what happens when the hand window is used and the input is slightly off bin. Okay. So, the ones in magenta correspond to rectangular window and the ones in blue correspond to hand windows, and in both cases the two tones used are 127.01 by 1024 Fs and 127.001 Fs by 1024, and as you can see still there is leakage in both cases, right, but the leakage when you use a hand window is much smaller than the leakage you get when you use a rectangular window, and this makes sense, right. I mean, how much improvement you must get is not immediately obvious, right, but the fact that you do get an improvement is, it makes sense, all right. Okay. And again, as you can see, as the frequency deviation goes from 0.01 to 0.001, the leakage in both cases reduces by 20 dB. And you know why, all right. Okay. Now that we have considered, we have seen the advantages of windowing, one might ask, what is so sacred about the hand window, and the answer is there is nothing really sacred about it, right, except the fact that if the input lies on a bin, then the hand windowed spectrum will have just 3 components, okay. And not surprisingly there are any number of windows that are available, right. In data conversion work, this is what is often done. If you are able to sync the input with the with the clock, and you are building what is called a Nyquist rate converter, then there is no problem at all. Leakage does not happen because they are synced properly and you use a rectangular window, right. Now, there are cases when you are not able to sync, okay, in which case you use one of these window functions. We will discuss more in detail what that is, right. There are also cases where the input is lying on a bin, right, but in addition to the signal there is noise, okay. in which case we have to worry about what to do. I mean, it might be okay as far as the signal is concerned, the signal may not leak because it is sitting on a bin, but there is noise in addition, right, and the noise being what it is, right, there is discontinuities at the beginning and the end of the record, and that will cause leakage, right. So, we will see all this in the next class.